So Stokes' theorem tells me that the circulation around a closed path in 3 dimensions of a vector field agrees with the surface integral of the vector curl of that vector field through any surface whose boundary is my closed curve. Any surface at all, as long as the boundary is the curve that I'm working with. So the first activity that we'll do here with this Stokes theorem is going to be just to get us some practice, first of all, thinking about the relationship between a parametrized surface and its boundary, which is a curve. The one way that we have so far to get curves that are a part of a parametrized surface is just to set one of the variables equal to a constant. Sometimes the curve that we get will actually be the very edge, the fringe, if you like, of that open surface, right? We don't have a closed surface now, we have an open surface, so it has a boundary that resides right there on the border, if you like, of our patch of surface. And so the first portion of this activity just has us getting some practice thinking about that relationship between a surface and its boundary. And so I've done some portions of this for us. So if the surface is the portion of the sphere x squared plus y squared plus z squared equals 4, so that's a sphere of radius 2 centered at the origin, and if it just consists of the points with z greater than or equal to 0, then what would the boundary end up looking like? Well, if I parameterize the sphere in the way that we know how to parameterize spheres, and then set z greater than or equal to 0, because my z-coordinate in my parameterization is twice the cosine of s, right? That means twice the cosine of s needs to be greater than or equal to 0. And so we're only going to get the s values whose cosines are positive. So only going to get the s values between 0 and pi over 2. Right? And so if I get just those s values from 0 to pi over 2, I'm going to end up parameterizing just the upper hemisphere. And the fringe, the border of that upper hemisphere, is going to happen at the place where s is equal to pi over 2, so on the equator. Another way to say that is that the border is going to happen when z is equal to 0. So the border is the equator of the sphere in the xy plane. And I can get a parameterization, it turns out, because that border corresponds to a single value of one of my parameters, s equals pi over 2. I can get a parameterization for the curve, which is the border, the boundary, just by evaluating my original parameterization by setting s equals pi over 2 to be constant. Right? And then I get this curve, which really does parameterize a circle of radius 2 in the plane z equals 0, centered at the origin. It gets a little bit more dicey if I do something else. So in this example, the same sphere, but for all the points for which z is greater than or equal to x. I think it would actually help to come up with a visualization for this real quick. So when we look at the sphere of radius 2 and the plane z equals x passing through the origin, we can see that this plane is also cutting the sphere in half. The problem is it's cutting it on a diagonal. And so parameterizing the boundary is going to end up being if you look at it from a bunch of angles here, looks like a pokeball actually. The boundary is going to be a circle, but that circle is going to reside within this diagonal plane. And so parameterizing it is going to be not quite as friendly as the parameterizations that we did before. In particular, if we look at this thing from above on the z-axis and we look just down at the xy plane, actually the outline of the boundary looks like it's not a circle, it's going to be an ellipse if I look from this vantage point. And we're going to see where that ellipse sort of comes out and the solution of this. So since the boundary is a circle of radius 2 in the plane z equals x, what I can do is just take z equals x and substitute x for z in the equation for my sphere to get myself started. That shows me how the x's and the y's relate to one another along the boundary, related by 2x squared plus y squared equals 4. So setting z equals x in the equation, x squared plus y squared plus z squared equals 4. And when I rearrange that, divide everything out by 4, I get x squared over 2 plus y squared over 4 equals 1, and I can use the sum of squares parameterization to get x over the radical 2 is cosine of t, and y over the radical 4 is sine t, for t ranging from 0 to 2 pi. And so if I solve those for x and y, I get x equals the square root of 2 cosine t, and y equals 2 sine t. So that's a parameterization of an ellipse that has a major semi-axis in the y direction of 2, and a minor semi-axis in the x direction of the square root of 2. So it's a little bit taller in the y direction than it is wide in the x direction. And that's what we're seeing here. It would be this ellipse. You can't quite see the bottom side of it, but there's sort of the bottom side of it. This ellipse is taller in the y direction than it is wide in the x direction. And then to finish the parameterization, we just have to remember that the z-coordinate and the x-coordinate are exactly the same. And so whatever is my x, square root of 2 cosine t, that same thing shows up again as my z-coordinate in this parameterization. So there's the parameterization for the boundary of this intersection of the sphere with the plane z equals x. So what I'd like for you to work on next would be to let's just do part B. So it's the portion of the hyperbolic paraboloid. This is the saddle surface, x squared minus y squared equals z, for x squared plus y squared less than or equal to 1. So here's our surface. This is the hyperbolic paraboloid z equals x squared minus y squared for just the x and y values that are within the unit disk in the xy plane. So if I look at this saddle from above on the z-axis, I'm seeing just the unit disk. So your task is going to be to find a parameterization for the boundary, the edge of this potato chip inside of 3 dimensions by using the information that's given to us here. So your speculation here was that we could parameterize the edge of this potato chip by just taking the polar coordinate parameterization and setting the radius of that parameterization equal to 1. So we have cosine s sine s, right? And then evaluating the z-coordinate by evaluating it using the x and y components of your parameterization. So cosine squared of s minus sine squared of s. And so this is now a parameterization of just a single variable, r of s ranging from 0 to 2 pi. So if I put that curve into our visualization here, just to make sure that it works the way that we claim that it does. So sure enough, when we place this parameterization into our GeoGebra, we find out that it is in fact tracing exactly the edges of this potato chip. I guess the single edge of this potato chip. Notice too that when we look at this from above, what are we seeing? We're seeing a parameterization of the unit circle, which makes sense if we just zero out the z-coordinate of the parameterization that you came up with. Zeroing out that z-coordinate will give us just cosine of s comma sine of s. And that is exactly an example of a parameterization for the unit circle, s ranging from 0 to 2 pi. So encouragingly, that's exactly what we see when we look in the xy plane. But when we're looking at this in 3-dimensional space, it's giving us exactly the edge of this potato chip. So nice work.